introduction. Good afternoon to respected Principal Madam, HODs, and the professors for giving me this opportunity to talk about the speech intelligence systems. So, as the topic is mentioned, speech intelligence systems, I would like to ask one question: what is speech intelligence? I want audience to respond if they are, because this is a post-lunch session and I don't want anyone to be so lousy. So I will ask some questions in between, and my talk is morely oriented not towards the research side, but it is more towards the application and the development side. So it will be a little bit interesting for the students. So what you are expecting as speech intelligence? What do you mean by speech intelligence? Any answers? Okay.
It helps in assisting us.
Okay.
Recognize our companions.
Let me change my question. See, what does speech intelligence means? By listening a speech or voice sample, what information do we get? Now I think it is easy. By listening any voice or any speech sample, you will get some information. So can you tell me, can you list out all the info, what all the information we are going to get? Okay.
Who is speaking?
Yeah.
And what are his emotions?
Yes. Yeah. In theoretical terms, what we call this information as metadata. Okay. So I can rephrase my question in technical terms, like what metadata does the voice contains. So we have a lot of metadata that our voice contains. So first let me go through the metadata information, what our speech is containing. As ma'am has mentioned, first information is regarding the speaker. So by listening the voice, we can immediately gain some information about the speaker who is speaking that. So the first information we can get is easy information is whether it is a male or female. So the technology that is involved in this is gender recognition. Okay. The second one, what we are going to get is if you know the speaker who is speaking, then you can identify that speaker. And the technology that is involved in this is speaker recognition. So based on this information, we have a technology called speaker recognition. Now, what more information we can get about speakers? We can also get the emotion, as your HOD mentioned, HOD sir. So there is a emotional state we can assess, like a person is happy, angry, or he's mentally disturbed, he is emotionally down. So this is what we call emotion. So this comes under emotional recognition. And this particular part of the research or the work is very important for what we call this doctors or even this police intelligence agencies. When a call comes, they want to assess the mental state. It should be automatically assessed by the systems. They want that kind of thing. Okay. Then if the speech what we got is a conversation, then we can also identify how many speakers are there in that conversation. So the technology involved in this is speaker diarization. So in speaker diarization, what we are going to do is if the conversation is more than one speaker, then it will identify how many speakers are there. It won't identify who that speakers are, but it will identify how many speakers are there in that conversation, and it will also tag from where to where speaker 1 is present and from where to where speaker 2 is talking. So this all information we can get from the speech. Okay, but is it what we are going to get from the speech? Speech is very rich of information, right? So we have so much information embedded in our speech. So the other thing is mostly widely known thing when we are known as speech systems means it is a speech recognition system. Means what it gives is what we want to convey, the content, the message, what we are going to convey to the other party. That is what is called content. So can we understand that content? The technology that is involved in this is automatic speech recognition systems, and the other one is keyword spotting. What is the difference between these two? In automatic speech recognition system, whatever we are talking, the corresponding text will come. So proper transcription of the whole speech is going to come. In keyword spotting, it is not the same. Just if you have any transcript, then only a particular word is present in the voice or not. So that technology is called keyword spotting. So where do we use these things? Like for intelligence agencies, they have hundreds of samples are there, voice samples. And there's a huge dump is there. And if they want to analyze, they have to sit and listen all those things. But do they require to do all these things? They want only those audio samples which contain some certain keywords like anything like bomb or any whatever may be the words. So for that, this keyword spotting is very useful. And you can always tell me that why can't we do the speech recognition, then why can't we search in the text? See, one thing is speech recognition systems are very costly affair. Now, costly not with respect to the money, but with respect to the computational facilities also. This keyword spotting is a lightweight threat compared to the automatic speech recognition. That's why this keyword spotting is also one of the emerging technology which is getting associated, coming out from this speech analysis. So any other information we are going to get from the speech? The third one is the language. So once you listen to this, so you can identify the language of the speech, right? Like I don't know the most of the South Indian languages like Tamil, Kannada, Malayalam, but I can identify this. If I get a speech, then I can say that this is Malayalam, this is Tamil. So why do we need this language identification? See, this automatic speech recognition, what I have spoken just before, those are all language specific. Means if I had built a speech recognition system for English, it will work for only English only. If I built a system for Telugu, it will work for Telugu. Now I got a sample. Now on which speech recognition engine do you give that sample? Whether it is, we don't know the language and all, someone has to sit and listen and tell that this is automatic, this is Telugu language, so feed it to the Telugu recognition engine. So for that cases, first we have this precursor as a language identification system. Once the speech intercept comes, we will identify what is the language used in that in that transcript. Then we will send to the corresponding speech recognition system. Okay, only these informations or any more information. So the other one is this forensics application. This is one of the important application called device identification. This forensics people require this application where from the given speech intercept, we can identify the handset also. So the technology is device identification. And these are right now so many papers are coming on these things. The device identification is one of the hot research topic. So these are all information what containing. So we can have so many, not only if anyone is telling speech recognition, most of us thinking that only automatic speech recognizer, but we have so many devices, so many applications can be developed using speech. Okay. And prevailing conditions, we have our COVID is there. So, and there is a research that is going on from the speech. We can identify whether the person is infected with COVID or not. Why? Because speech comes from the throat. So the COVID is affecting our throat. So the way that we talk, okay, that is getting affected by the COVID. So now I am seeing a lot of papers are coming on identifying a person whether he is infected with COVID or not. So that's what we are using our technology in our real time. This is where we are using our technology in real time applications. Okay. So now I said that speech is rich of information. Then why don't we have so many applications are there, but all are these applications, have you seen any of these applications so widely used? No, right? Only nowadays we are getting this automatic speech recognition systems after the advance of neural networks. Why we are not getting this? So many applications are there. Everything by listening a speech, a human can identify all these things. Why these are not been built as an applications on a devices? So let us see that. So this is a computer representation of a speech, and this is the this is one type of representation where in x-axis it is a time and y-axis is the amplitude. Means as time goes on, how the amplitude is varying. This is the time amplitude represent of the signal. Now I would like to ask a question. What is same between these two sounds? Can anyone guess? So this is what our computer sees, right? As a human, we will listen them, but this is what computer sees. And from this, after seeing this, they have to give us what we want. Like whether you want a speaker information, you want speech information, You want gender information. So let me play these sounds.
We are attending a tutorial.
Okay, this is the first sound.
We are attending a tutorial.
So by listening now, you can identify that this is the same speech from two different speakers. But by looking at this signal directly, time amplitude representation in a computer, we can't differentiate, we can't able to guess what is same and what is different. Even though the sounds are different, the waveform is totally different. It is not looking same, right? Little bit similarity is there, but it is not exactly same. There is another representation in computer. This is called time frequency representation. We call them as spectrograms. Okay. So what these spectrograms? I will explain you this spectrograms first. See, as we are speaking, different sounds will have different frequencies, right? All sounds won't have presence of all the frequencies in the sound. Like if we see this first word, we have only dominant 4 frequencies are present, right? In this other sound, other frequencies of some around 3 to 4 frequencies are present. So what it says, this representation says is along time, what all different frequencies are present in that speech signal. Okay, so this is what called time frequency representation, and these are called as spectrograms. Now that is the one previous slide I have shown you, the time amplitude representation. We can't able to guess what information is there in this, but from this, can you guess what all are same and what is different? Again, spectrograms, they give the frequency. If it is the same words, then you can see that the frequencies present in that words will be the same, right? So this is again the same speech from two different speakers, but what we can say is some people who can read the spectrograms, they can say that these two are same sounds, but they can't able to give any information regarding the speaker because that is not clearly visible here. But as a humans, we can do that, right? So I would like to show one more thing. There are two sounds here. Now by seeing this, now can you tell me what is the same in these two sounds? Anyone, any guess? At least after giving that first introduction.
Amplitude, sir.
No, see, amplitude is what is visible to us. I'm asking, we have some metadata, right? In speech intelligence, I've told that there are a lot of metadata embedded in the speech. By looking at this time amplitude representation of the speech, can we able to say that this is so-and-so speaker or this is so-and-so speech? Are we going to get any kind of information? Or at least can you tell me what is same in these two things? Are these two same sounds? Okay, let me play it.
Attending.
Yeah.
Attending.
The sound is
Attending.
okay. These are the two same sounds, but from the same speaker, right? Now, what I want to convey is previously we have two sentences uttered by two different speakers. So even though speech is same, the speakers are different. So the signals are different. Now here speech is same, even the speaker is same. Again, the signal is not same. See the amplitude difference here. It is up to only 0.4 and here up to 0.5 it is going, right? It is maximum amplitude is up to 0.4 here. This is 0.5. Means what I want to convey here is the speech, even though it is the same, it is varies across different speakers and it varies for the same speaker for different sessions also. That's why the variations in the speech is very high. So that's why all these days we don't have so many applications, even though speech is giving so much information to the humans, right? Even speech is giving so much information to us, we can't able to build so many applications. Why? Because the input is highly variable. Okay, so that is what my point is. This is the other frequency time representation of the same words. By looking at this also, I don't think we can able to guess that these are all same. Okay, now we have seen that why the speech systems are not coming, because of highly variation across different speakers and the same speakers also with different sessions. Now I would like to draw, we have so many systems with respect to text. So how speech processing is different from text. A small analogy I will give you. So now there is a sentence here. So I would like to ask how many words are there in this sentence. So by looking at it, we can clearly say that we are attending a tutorial. It's a 5-word sentence, right? Now I will show a corresponding signal. Can you tell me how many words are there in this signal? So by looking at the signal, you can't able to say how many words are there in the signal unless you listen. As a human, we listen and process it. That is a different thing. But mission is seeing this. By seeing this, can we guess how many words are there in this? But by looking at the text, we can able to guess, right? Not guess, we can able to say that. So here the words are same thing. We are attending a tutorial, right? Now I will ask one more question. What are the word boundaries? Can you tell me? Can you identify the word boundaries? Even though after telling that the speech is corresponding to this text, can you tell me by looking at this what all words represent which all portions of the signal? It is difficult, right? But for our text, we have clear word boundaries, right? So this is where the boundaries for this corresponding speech, right? This is the one particular problem if speech is continuous and we don't know the boundaries at all. Okay. I would like to do one case study of identification with respect to one word. Okay, not whole speech, only one word. Let us take attending. So how many words are there? How many letters are there in the attending? There are 9 letters, right? So your search space with respect to your input is order of 9, right? Attending means you just search for 9 times and you will identify that this is attending. Okay, but correspondingly speech is 600 milliseconds. Okay, attending word is spoken for 600 milliseconds. Now 600 milliseconds means in computer how many values are representing that 600 milliseconds? Now I'd like to introduce one term called sampling frequency. Okay, because most all are you from computer science department, you don't know these words. So sampling frequency is the term which is a basic term used in speech processing. So what does it give is, see, speech is a continuous signal like this. Now when we are coming to the computer, computers cannot hold the continuous signals. So we will discretize. Means after every time period, okay, we will see what is the value of the signal. Okay, so this what we say this doing sampling is, this is called sampling. The technique what we do is called, we will sample the signal and we'll see the what's the values of the signal. So at what rate we are going to sample the signal? That means per 1 second how many samples we are going to take. So the sampling rate will tell me how many samples are there per 1 second of speech. Means if you are speaking for 1 second, how many values it is cutting. So if you take generally, we have 8,000 sample, 8K sample, 16K sample frequency signals. So if we take 16K sample signal, it will turn around to be 9,400 samples. Means one attending word in the computer, we have 9,400 different values is representing our attending word in speech. In the same case with respect to text, we have only 9 different letters, right? So now such space is increasing from order of 9 with respect to the input. This is only with respect to input. Here we are searching for 9 times. Here we have to search for around 9,400 times. Okay, the value 900 values we have to search. So the search space is increasing from around 1,000 times for only one word itself. That's why the speech processing is very highly computational. Okay, so now I would like to give a summary between the text and speech, printed text and speech recognition, how the machine is doing. See, for printed text, we don't have any variances. Means the printed text, we doesn't find much variance. Only we have capital letters and small letters. If we once cater them, then it's finished. We can identify the printed text. But speech, just now I have mentioned that it is, I shown that it is varies with respect to different speakers, and with respect to the same speaker also, if you are speaking for different sessions, it varies. And in printed text, we have clear word boundaries with spaces. But with speech, we have seen that there is no clear boundaries, right? And then low noise. So while typing, printed text doesn't have any noise at all. We have clearly, we can see that there is it won't get disturbed. But with respect to the speech, it is highly disturbed with the noise. As your HOD sir is mentioning, it is very, not only variances across speakers, but with respect to the background noise also, speech is varying. You can do your small experiments. Now everyone is having your this thing, right? Headsets. Just record the words, some word without a fan, then switch off a fan and record and see them in your MATLAB. So that both the signals are totally different. Okay. This background noise is one of the culprit which is hampering all the systems based on speech. Then the other thing is the distortions. So while sending, see, whatever data we are having, we won't keep it with in your suitcase, right? We have to transmit across people. We have to transmit. So while transmitting text, there is no loss at all. But while transmitting speech, you have just now seen for one word only, we have 9 letters there and 9,000 values here. So for one letter, it is 1,000 times increment is there. So like that, if you are sending a speech, lot of bandwidth it will consume. So what generally is the speech transmission happens is they will encode at the sending side, then they will send, and at the receiver side, they will decode them. This is what they call as speech coding. There is one other research area what called speech coders. So how much you reduce your input and send to the other side, and without any loss, you have to play back the signal. So this kind of transmission will introduce a non-linear distortion. Non-linear distortions means you cannot bring back the distortions. We cannot assess what are the distortions we are going to get into that signal because of the transmission. So this will have a huge effect on our recognition systems, right? So this is the one thing that hampers our recognition systems in speech. And again, I told you here only low computational machine learning algorithms are enough for identifying the printed text. But with respect to the speech, we need very highly computational intensive algorithms. Okay, so till now what I covered that speech is highly variable across speakers and even with the same speaker. Now, why it is different? Why it is different and difficult from the text identification, right? Now, the third thing we will see that how, as we are building here missions, speech systems for missions, right? So what machines can do and what humans can do with respect to the speech, I would like to draw some analogy. See, with respect to humans are very better in handling uncertainties. That means, right now, I hope that my voice is very clear to everyone. Now, if suddenly I will put on some fan or some external noise is coming, then also you can easily identify still the same person Mr. Anil is speaking, right? But is it the same case with missions? No. If a small additive noise, this is the additive noise what we call. So if a small additive noise is there, then our systems will perform badly. Okay? And then humans are very accurate. Means if humans are identified, this is so and so person, or he is saying so and so, means speech recognition, he is telling me so and so, means he is very accurate in identifying that. But our systems are missions are not so. But where humans are lacking is they lack consistency. What does consistency means? Means suppose after this session, if I call someone randomly and ask, hi, can you recognize me? Yeah, you know my voice, you are listening me for more than 1.5 hours. So immediately you can say that, you may be the Anil, right? But if I call you after 1 week and I'll ask, hi, do you recognize me? I don't think you will be able to guess that I called you, right? Because humans can't have that kind of thing in your mind. Is that kind of memory is not there. So that's why humans are not consistent. But what machines can do? Machines are highly consistent. So today, once it is, my model has been there, Anil's model is there. If it's a speaker recognition system, Anil's model is there. Today you give, after a week, after just 10 days, 20 days, whenever you give me the speech, it will tell that, this is Anil, right? That consistency is there in missions. And again, missions can handle huge volumes. Again, we will take speaker recognition as a simple thing. Suppose as a person, how many people you will identify? 10 people, 20 people, or if you are extraordinary, then you can handle up to 50, more than 50, right? Now, can you handle 100 persons? Means, can you recognize 100 people at any point of time? You cannot do that. As a humans, we cannot do that. but machines can handle thousands. Even there is a, I think IBM has shown that they have clearly classified 10,000 people in one system, 10,000 people, right? But what they lack is they lack the intelligibility. So they cannot handle uncertainties. So that is where the humans lack. So what is our aim in developing the speech intelligence systems is to take the positive attributes of both human recognition and machine recognition and develop a machine system application based on speech. This is our aim. So now we know what is our aim, but what are our challenges? So we can say that, yeah, as a human being, I can do this thing. I can identify the speakers. I can identify the speech. So many metadata I have given. So we can do that. But why machines are can't able to do that? The first primary thing that is hampering is the quality of the speech. Okay. So what affects the speech quality? The first one is environmental noise. You can easily see that the signals, the recording signal without noise and with noise, it varies. So, and this environment is not constant. Today you are in a room, tomorrow you may be on the road, tomorrow you may be in the railway station. All the noises are different, right? So this environmental noise will have a huge impact on the quality of the signal, and this will affect our recognition systems. Okay. The second thing is the recording instruments. See, we have people are telling, right? We can see that this is a high quality mic, this is a low quality mic. Why do we have this kind of segregation between the quality? The quality that is good, the high quality microphones will give me a good recordings. Okay, so what does it happen? The microphone that is used for your recordings will also have an effect on your speech signal. Okay, so this is what we call that recording device variabilities will come into the system. Okay, so as the device is varying, your signal also will get varied. Okay, so this will also hamper the signal quality. The third thing is channel effects. So the speech what we are recording, we won't keep it in our safe. We have to transmit across. So while transmitting, I said you there are this speech coding effects will come, all the channel effects will come. So these all three things are primarily, not only these things, even more may be there, but these are the primary things which affect our speech quality. Okay, then what are the challenges? The other challenge is inadequate data. So why we need data? We need for building a systems, we have to train our system. So our training is based on statistical training. Statistical training means from a data we estimate some statistics, right? So for estimating statistics, we need enough data to represent that particular class. In speaker recognition, it is the each speaker. In language, it is each language. Each class is one language, right? So where do we have enough data to represent that class? So we don't have. So the problem is we don't have enough data to represent the class what we are training for. The other thing is providing robustness under mismatch conditions. So mismatch conditions arise like this. Suppose you want to identify again. I will take this the simplest thing. That's why I'm again and again saying speaker recognition. So in speaker recognition, you have trained a speaker with a microphone data, and all of a sudden, that person's speech is being recorded over a landline telephone. Okay. Now you have built your model using a microphone data, and your test data comes from your landline. Now both devices are different. Now what we call them, these are mismatched conditions. Now as a human being, you can identify, but missions, since we are estimated our statistics using microphone data and we are testing using our telephone data, definitely there is a probability of error. So we need to see that what all conditions we are going to use our systems. So and if suddenly some mismatch condition comes, will our system will able to handle? So that is the one thing which hampers our speech-based systems. Okay. Now the other thing is performance scaling. Now what do you mean by performance scaling? Suppose you have a system which is recognizing for 10 speakers. So 10 speakers, you may say that it is recognizing very good. It is having an accuracy of 95%. Okay. Suddenly you are increased it to 20 speakers. Will it retain the same performance? Or suddenly you increase up to 100 speakers. Will it remain the same performance, 95%? Because all this data is a overlapping data, there will be a performance hampering. So definitely the performance will come down. So as we scale, means uh, as we scale our input, like from 10 speakers to 20 speaker identification to 100 speaker identification, the performance should always remain same. That is the one of the challenge. With respect to the keywords, right? Keyword spotting. Now you can identify 10 keywords. If you are going for 100 keywords, 200 keywords, the performance should always remain same. That is one of the challenge while building your system, even for number of languages also. The other thing is our computational challenges. So on where you are going to put your application. Is it a small device? Then small device will have small computational power. Okay, if you are having computers, then it's fine. But you want everything to be only handheld devices right now. Can we put our applications on those things? This is also one of the challenges you have to keep in your mind while building your systems based on speech, because they are highly computationally intensive. Okay, fine. Now, why these are all challenges are coming? Why? I said I list out these challenges, right? Why these challenges are coming? Why? Because primarily present day technology is based on statistical approaches. What does statistical approaches mean? See, statistical approaches means we have a data and we estimate some statistics from the data. That is the main culprit which is hampering all these applications. Why? Because we are estimating data by seeing the data what you have provided for training. Now, the estimated statistics, will they guess for all other kind of, means all other variabilities, not only present in your training data? It is very difficult. That's why the machine learning, mission systems, all the speech-based systems have prone to be errors. That's why they generate false alarms. There will be misdetections, because the primary culprit is our statistical approaches. That is what the technology we have. We have to live with it. There is no other go for us. So suppose if you take speech recognition, okay, I will take two case studies. One is speech recognition. You all know that we have Siri and all these things. They recognize the voices. Okay, now suppose I built a recognizer for English. Let take it as a Telugu. Telugu recognizer is there. Now, if I ask any person to speak in Telugu, do you only speak in Shuddha Telugu? You will always get some English words in between, right? We can't stop that. We cannot stop target to talk only in Telugu. Now you have trained your Telugu engine based on your Telugu dictionary. Now suddenly some English words are coming in it. Now how will your recognizer will able to handle that? This is one of the challenges what we face for while building the speech recognition system. Okay, and not only that, the other thing is nouns, handling nouns. What do you mean by nouns? Nouns means names of the people, names of the places. So these things won't be there in our dictionary, right? And suddenly a new place can be there. We cannot restrict anyone to put only from this list only. You have to select the names, right? It can come from anything. So this is also, now our engine is not trained for these words. Now how you will identify? So these are all comes under called out of vocabulary words. Okay, the recognition engine, how you handle this out of vocabulary words in speech recognition. This is one of the primary challenge for the speech recognition engine builders. Okay, the other thing is pronunciation variants. You take, like, suppose I have built a Telugu recognizer. Okay, now we have our North Andhra dialect, Godavari dialect, again Krishna Guntur dialect, Nellore dialect, Telangana, Rayalaseema, so many dialects in one language. Now suppose you have built your system. Will it identify all these kind of pronunciations? Will it cater your system? What you have built, suppose you have built, right? These things, what all pronunciations are, what are dialect variations are there in that language, we have to take consideration while building the system. If you don't do that, then that will hamper at some runtime. You may not anticipate now, but a test file may come from one of the sample which you might not have seen during your training. Then your recognizer performance will come down. Okay. Similarly, we have speech recognition system. I have explained you intra-speaker variability means the speaker will have variations himself. Now he is speaking, and after 1 hour, if you ask him to speak same thing, and if you analyze in computer, both look very different. And the other thing is, due to the health conditions, a human's voice will get changed. You know that, right? And Due to health, other factors may not change, but definitely with respect to the cold and cough, your voice get changed. Once your voice get changed, can we identify the same speaker? So, these all will affect. So that's why this COVID research also has come into the effect. Why? Because they want to see that what all they are having three classes here: a person with normal, person having cough, and normal person having cough but having COVID. These are the three classes. It's a three-class problem. They are trying to handle it, and all the papers what are publishing is handling this three-class problem. They want to give a solution based on speech, whether by recording a patient's voice, can we guess whether this person is infected by COVID or not. So a lot of information is there, as I mentioned. So saying all these things, now I would like to ask a question that so many variabilities are there. So don't we have any speech systems? No. The answer is no. We have systems. Then how we have built these systems? The answer is it is a targeted service, right? Only targeted service. Like I think our HOD sir has mentioned, or Dr. Ramanjana Viranelu has mentioned that in a cars while driving we are having the speech based voice based this software which is in your cars to drive, right? Now you say that this particular voice based driving solution is only aimed to take the commands related to the driving only. They will do that, but for this driving commands they will have high probability of recognition, right? So if you fix your target, then you can have the speech-based system with very less false probabilities. I'm not saying zero probabilities, but we have very less false alarms if you identify your target and if you try to build your system for a particular target only, right? So our Google Voice, Apple Siri and all, I don't know whether you might, have you ever tried these systems in your standing on a road where you have huge noise? Definitely it will keep on asking, sorry, I can't understand you, can you repeat? Why? Because they are mainly developed for closed room environment, right? If at all there is a problem, immediately it will raise the sorry, I couldn't understand your command, right? So the speech systems are there for targeted services, right? It is now, if you want out of blue moon, under the cloud, everything should be identified. It is very difficult because of the variations that exist in the speech. And even speaker recognition also, biometric authentication systems. Why we are not using this biometric authentication? That means speech-based biometric authentication. Why? Because if a person suddenly gets cold or cough, and we have probability of misrecognizing. At that time, if you are not allowing that person to the critical area, then it is useless. That's why this kind of solutions are not there. But lightweight applications, like I've seen recently in Standard Chartered Bank IVRS. So they have introduced this biometric authentication based on speaker. So you have to identify where you can have your speech-based systems. Then definitely with less false probabilities, we can build a system. But in general purpose applications, it is not difficult, but it is not, I cannot say it is, we cannot build it, but it is little bit difficult to build for a general purpose. But targeted services, we can always have the speech-based system. So now, giving all this introduction, I want to go a little bit deep into the systems, how the speech-based systems are there. So since it is a speech-based system, this is the block diagram of the speech systems, any speech systems. Okay, we have so many systems like gender identification, speaker identification, speech recognition. So for all the systems have this block diagram. So what we take as input, because speech-based systems, we take input as speech. Then first what we do is we extract the features. Okay, once we extract the features, during training, what we do is we will model. Training means it is like a registration process. So if I want to recognize you, I have to see you before that. I have seen this person and his name is so and so. Then tomorrow if I see somewhere, then I can identify, hey, you are so and so, right? So like that, even humans also requires the registration. The registration process, what we call as a training. So in training, what we do, once the features are extracted, we will build the models and we'll keep in the system, right? And during testing time, what happens is, again, we have to extract the same features what we used for more training. So those features we extract, and what we do is we will do the identification with the existing models. We will do some scoring mechanisms, and we will say that so and so I got the high probability, so this test speech may be so and so. So now I'd like to ask questions here, small questions like, for speech speaker identification, your models will be the speaker models, like one model for one speaker, second model for second speaker, and all. For language also, each model will have one model. Now tell me, what will be the models for speech? Any answer? For speech, what will be your target models? For what you are going to build models? Okay, let me go ahead. See, speech is consisting of a basic concatenation of basic sound units. Like for English, we have 26 alphabets. With the 26 alphabets, we can write any word, right? Like that, any word we are speaking, they are built with a small units. Basic sound units we call, they are called phonemes. So these phonemes, they get concatenated and we hear a word. So for speech recognizer, what we do is we build models for phonemes. Generally, different languages have different set of phonemes. Typically, they are around from 50 to 75. Phonemes will be there per language. It varies per language. Okay. Now, this is a case study for speaker recognition. If we have two different speakers, we extract the features and models. We have one model for each speaker. And during identification, what we do is we use those models, extract the features, and then we will take a decision which speaker it is based on some probability, computing the probability with respect to the features extracted and the models what we are having. Fine. Now, the first step of what we are having for speech-based recognition systems is feature extraction. So saying that, what should be our ideal features? Okay. Now our ideal features what should your ideal features that should contain while building your systems? So the answer is, the kind of features that you extract should be distinguishable, right? We have two applications here. I will take speech recognition and speaker recognition. Now for a speaker recognition, you will identify a speaker based on the way that you speak, the style of speaking, the pitch information, the rate at which he is speaking. These are all things you will gaze and say that this is so and so person. But will those same features are used for speech recognition? When you are understanding what is the content in that voice sample, these are not used. These are not at all used. So we have to identify that feature set which is distinguishable for your target. So that is the important thing. Now, once you identify, yeah, these are the distinguishable, now we have to see whether is it easy to measure. For suppose I can say that for a person, if you want to identify, I will say that the distance between the two eyes is unique for each speaker. So now I gave this statement. For any human being, the distance between these eyes is unique. Now, will anyone will always go and measure that? Is it easy to measure the distance and say that this is this much measure has come, so he's so and so speaker? So like that, do we have computational methods to extract those features which are distinguishable in your first step, right? You identify some set of features, these are quite distinguishable. Now, can we able to measure them? Is it easy to measure them? That is also we have to see. If you can't measure them, then we want it is useless for us. Those features, even though they are distinguishable, it is useless for us. Now, the other important thing we need to the noise and external distortions, right? Where if they whatever features we are extracting, if they are easily getting distorted, then what is the use of those features? Now the sample with small noise will totally distort the kind of features that you are extracting, then they are useless, right? And it's the same thing with respect to the health. If they are varying with respect to the health, then they are useless for us to build our systems, right? The features that we extract should be robust against these all aspects. And suppose if you take speaker recognition, the kind of features that we extract should have a large variability between speakers. Means the kind of features that are extracted for speaker 1 and the features for speaker 2 should be have a large variability and small variability with respect to the same speaker. So these are the ideal feature sets. So by saying these ideal features, the features should have these ideal conditions. Do we get these things? For speaker recognition, let's take for speaker recognition, it is like I said you, the rhythm, the way that we speak. Okay, the raise and fall of the voice, the accent, the pitch, these all I'm telling. With these things, we can identify a speaker. Now, what all will affect the speaker identification system? The age and health. As age grows, the voice of the persons will get affected. Health is definitely, it will affect with respect to cold and cough. And the other thing that affects is the spontaneous and read speech. Means if you are speaking spontaneously, the speech will have a different characteristics, and if you are reading, you will be very conscious. The way that you read by seeing a text and the way that you talk spontaneously have a different characteristics. So that is one of the thing which is very important for speaker recognition. And definitely we've seen that background noise and recording devices, they will have their own effects. So while building the speaker recognition system, we have this kind of feature characteristics and we have these challenges to be kept in mind while building. So now I will go a little bit deep into the technical aspect because I have given the introduction. Now I'll go deep into the technical things. Sir, Dr. Veeranjana Garu, shall we take a break as mentioned or shall I continue?
No, sir. If possible, we can continue, sir.
Okay, then I'll continue because from here, little bit technical side, I'm going into the uh, talk. Okay.
Sure, sir. Sure.
Fine. Now, as we have seen what all the challenges we are facing while building the speech recognition systems, etc. Now, I will go deep into the things. We have seen the speech systems have feature extraction, modeling. So now in speech extraction, we have to extract the features. So in particularly for speech features, they are classified into 3 different variants. They are called short-term features, mid-term features, and long-term features. So as the name suggests, the short-term features are extracted from very small duration. That is only 10 to 30 milliseconds of data. So what these features describe is, they describe the acoustic properties. Acoustic means how we are producing our speech. Okay, these will describe the acoustic properties, means how we produce the speech. Then we have the midterm features. The midterm features are extracted from 10 to 100 milliseconds of data. Okay, so it's a little over longer duration. So what information they give is, they give the rhythm, the way that we are speaking, the pitch information, the prosodic information of the speaker. So these kind of information, these features will give. They are called midterm features. And long-term features. See, long-term features are, as the name suggests, they are span over a conversation around 3 seconds. Okay, these are all milliseconds. Here, 3 seconds kind of speech we will extract. They give the pronunciation, accent, this kind of information of that speech. So why they categorize these 3 is, as we go from short to long term, it is very difficult to extract the features. The second aspect, is it easy to extract the features, is also important. Even though pitch, pronunciation, accent are very easy to distinguish the features, but it is very difficult with the existing technology what we are having. Right, with the existing technology, it is very difficult to extract those features. Right, so that's why most of the features, speech features, are based on the short-term features. Okay, these long-term, mid-term, and long-term features are also there. There is some research and papers are there. You can see it, but they are very difficult to extract and they are very susceptible to the noise. That's why all the systems are based on short-term features only. So what all different features? These are all short-term features are there with respect to the speech. So there is a list of, in literature, you have a lot of features like linear predictive capture coefficients, line spectral frequencies, perceptual linear prediction coefficients, MEL frequency capture coefficients. This is the important one. Bottleneck features, this is also. Then we have recently D vectors and X vectors are there. Okay. So these are all short-term features only. I concentrate in my talk this MEL frequency capture coefficients, which is widely used. Okay. And bottleneck features also I will give an overview. So I have told that we are extracting the Mel frequency coefficient, Mel frequency capsule coefficient. So how they are relating to the physical means always we need to have a physical representation of what these are. We are extracting some features from a signal. So what they physically represent. So these Mel frequency coefficients, the theory behind them is they are extracted based on the principle of how the humans produce the speech and how they pursue the speech, means how they listen the speech. So they took into the consideration of how a human produces speech and a human listens the speech. Based on that, they have designed those Mel frequency caption coefficients, right? So first I will explain how the human will produce the speech, okay? Here, what happens is, this is our skeleton of the production system of a human, where we have lungs. From the lungs, what we do is we'll pump the air. So once we pump the air, so from here, it will pass through and come out of the mouth. So what we call this is a vocal tract, okay? So this vocal tract is having two things. One is a nasal cavity and the other is a oral cavity. Means we have two paths. One is nasal path, other is a oral path. Okay, both combinedly called as vocal tract. Okay, now what happens is we are pumping the air and we are getting sounds outside. So the pump, when we are pumping the air, it is a constant air, but output we are getting variable output, right? So how we are getting the variable output? We are listening different sounds. So how it is coming? Why? Because of the vocal tract. This vocal tract is the one which is actually varying the input and producing different output. Different output means different sounds. So what this vocal tract is consist of? If you go from outside, so first we have lips, then teeth, then tongue, then we have the nasal path. So these are all things, okay? They all constitute a vocal tract. So the way that you position your tongue, your teeth, your lips, so the way that you position your vocal tract parts, different parts are there, right? So these all things will produce the different sound. You can always see that ah means you open and just pump the air. E means what you do, you position your mouth in some particular fashion, right? So that's how the speech is getting produced. So while producing these things, why we are listening different sounds? Why? Because when we position our mouth in means vocal tract in different positions, we produce different frequencies. So different frequencies will give the different sounds. Okay, presence of different frequencies will give you the different sounds. So that's why in the second slide I shown you the frequency representation, time frequency representation on the computer, right? That is where the time frequency representation will give some idea on how we are producing the speech. So that's why this human production system is considered while extracting the features. Okay. The other part is your ear. How our ear is perceiving the sounds, different sounds. So ear is what the ear is. We have divided. The ear is divided into mainly three sections. One is the outer ear. This is from here to here. Then the inner ear and middle ear and then inner ear. So when we pursue the sounds, what we do is this outer ear is just a carrier. It will pass the signal here, and this inner ear contains what is our eardrum. This is eardrum. Then it has some three bones. So what happens is the signal goes here and hits this eardrum. Then eardrum will move the three bones of our inner middle ear, right? Once they displaces this thing, what happens is the inner ear consisting of a spiral structure. You see this, what we call it is as a cochlea. This cochlea has a liquid inside it and there are hair cells on above. So what happens is once the eardrum, the sounds comes and hits them, then these three bones will hit this cochlea. Then the fluid inside the cochlea will move across this spiral structure. Okay. Now what happens is the different frequencies, I said that each sound will have different frequencies. So this cochlea response is frequency based response. That means for different frequencies, different section of the cochlea will respond. So once for particular frequency, if this frequency is present in that sound, then this cochlea will respond and the hair cells will start vibrating on that cochlea. Okay. So here that hair cells will get vibrate and they will generate the electrical signals to your brain. This is how telling that this particular frequencies are present at this time. That's how they give the signal to your brain. Okay. So that's how we perceive the sounds. Okay. The way that we how we produce our sounds and how we pursue our ear, these two things we are taking into control. Now the perception is not linear. That means what is all the frequencies are not linearly pursued. Suppose if I give you a signal, if I give you a signal with 100 Hz and 200 Hz, then I say that are these same or different, then you will clearly say that they are different, sir. But if I play 2100 and 2200 Hz signals, two different signals, only single frequency, then you will say that both are same. And that means what? At the lower frequency range, humans are capable of distinguishing different sounds, frequencies. But with higher frequencies, they generalize them, means they group them. So ideally, the response should be linear, but it is not linear. It is little bit log scale, non-linear scale. Okay, so this is the log scale, but humans' response is not even log scale. This is called Mel scale or bar scale. So the response of the ear is similar to the Bark scale, more or less similar to Bark scale and Mel scale. In literature, generally we use this Mel scale more. That's why we got that Mel frequency. Why that name? Because we are applying the response of the ear. Ear is having a non-linear response, so that's why we are using this information while extracting our features. Okay. So now I will explain a Mel frequency critical questions. You might be thinking that this is a signal processing, everything is electronics. Don't go by that. It is only 5-step thing. Easily you can implement in your MATLAB. Only 5 steps. The first one is take the input signal. The extraction of Mel frequency quotients I'm explaining now. It is only 5-step process. You take the signal and you do, the first step is windowing. What does windowing means? Nothing, it is only breaking the signal into small units. Why do we need to break the signal? Because I said these are all short-term features. Means short-term means we extract the features with short duration, means 10 to 30 milliseconds data. In 10 to 30 milliseconds, if you take 16,000 samples, means 16,000 sampling signal, if you take, it comes around 160 to 320 samples. Means you have a series, sequence of numbers signal, right? You take first 160 samples, then take next 160 samples, next take 160 samples. Means you divide the signal into different frames. What we call them as a frames. Okay. Once we divide the signal, if we don't, what happens is, if we take the first signal from here to here, second frame from here to here, since speech is a continuous signal, we will lose the information at this intersection, right? So generally what they do is they take the overlapping frames. That means the first frame starts from here to here, and the second frame starts from the middle of here, n by 2 to next, from up to n samples, again from here to here. So these are called overlapping frames. And why? Because we don't want to lose any information at the intersection. Okay. Now, after doing this, there is in windowing only. In this windowing thing, what we do is we will apply one filter. Filter is just multiplying a set of values with this signal. Just multiply this signal, this set of values. They are around 160 values. If the window is 160, you have 160 values, you multiply both of them. Why we need to do this window? So this is a Hamming window. Why we are doing it? Suppose you are taking a single frequency signal like sine signal. So once you apply Fourier transform, means what we are doing in Fourier transform, we see that what all are present. Fourier transform will give what all frequencies are present in this input signal. Okay. So in this signal, it is a single frequency. So ideally we should get a single value, but we are getting a lot of other frequencies present in this. Why? Because we have cut our signal very, means there is a clear cut here. There is no smooth cut. So because of this cutting, they introduce some high frequency components into the in the frequency domain. So what they do is if you multiply this window on that each frame, then this input will become like this. And then your Fourier analysis will give you a single peak. That's why we are doing it. With respect to computation, nothing. You break your signal, Hamming window, directly you give Hamming means in MATLAB, you will get this window. Oh, set of 160 values, the size, if Hamming of 160, you will get 160 values, multiply these values with this window. So your first step is finished. So you will get speech frames. Okay. Now, once the speech frames are over, what you have to do, we want frequency representation. This is right now still in the time representation. Now we want frequency representation. So we apply a Fourier transform. So we will apply discrete Fourier transform. So what we get is our spectrum. You have 350, 320 samples, my window size. So this is the speech signal. Once you apply DFT, your output look like. Simple FFT, one command is there in MATLAB. You apply on each frame, you apply FFT. The second step is over. So you will get this kind of output. Okay. So what it shows is for this speech at this time, you have these frequencies present. Remaining other frequencies are very less present. Okay. Only these frequencies are present for this signal. That is what we are getting with Fourier analysis, right? Okay. So if you combine, this is for one frame. Now, if you combine all the frames, we will get the spectrogram. This is what I have showed you in my earlier slides. So for this speech, you are going to get time, frequency, the energy is in the third dimension. This your color coding will show. Red color will have shows the high energy, means the peaks, right? These peaks are visibly here, clearly visible with the red color. Okay. This is how the spectrum, if you are seeing across the time. Okay. Now you have done your two steps. The third one is once you do the spectral analysis, that means you got the information of your production system, right? Now, once you got that information, we have to see our perception system. The perception system, what we have, it has a nonlinear response. So what we do is that Mel frequency warping, the step. So what we do with this thing is, this Mel frequency, I said that lower frequencies we can clearly distinguish, but high frequencies we will club them. Yeah, 2000 and 2100 Hz, both are more or less looking like similar. So similarly, what I do is for lower frequencies, I will club the lower frequencies with very less number, with higher frequencies, high number. That means here from 0 frequency to 4000, 8000 frequency, this is what our DFT output, right? This is my DFT output, 0 to 8000 frequencies. So we will apply triangles. This triangular bands. You can even apply square bands also. There is no restriction, but most popular is triangular bands. Different shapes can be studied. And there is a paper which studies different shapes of the different shapes. But most popularly, people have used this triangular band. So triangular shapes are applied. So what we are doing is just apply this triangular bands on this DFT output, and you will get the values. So what we call them as, they are called Mel bank values or Mel spectrum. So this is power spectrum. This is Mel scale power spectrum, because we combined some frequencies. The way that our real responses, that's how we combine the frequencies. Okay. Now after that, our steps are simply apply log and then do inverse Fourier transform, which gives you the Mel spectrum. The simple things, just for each and every value you apply a log, and there is a DCT like FFT. You again IFT is there. You apply one command, you will get your Mel spectrum. So these are your Mel frequencies. Okay. So it's a 5-step windowing DFT, then applying Mel frequencies, then log and DCT. These 5 steps will give you your Mel frequency capture coefficient. So you need not fear that this is not our computer science work. So only 5 steps will give the features. Once these features are there, now you will come to your modeling part, which is our computer science work. Okay. So don't get hesitated. That's why I'm seeing students doing less projects on speech. Why? Because they think that there is some theory behind the features which we want to understand. Simple theory, the theory is how humans speak and how human listens. That is the theory behind the features, and that features are extracted using these 5 steps. Once you do this in MATLAB, you will get your features. Okay, this is the speech waveform, corresponding spectrum, and your Mel frequencies. Now, how we are reduced. See, each frame we are taking around 320 samples, right? The 320 samples, if you apply 256 bank, 256 point DFT, you will get 256 values. Then if you apply some triangles, right? You are applying the triangles. So the number of triangles varies from generally 25 to 40. So finally, per frame, you are going to get from 320 samples to 28 values. From the 28 values, you take only first 12 things. There is some theory behind it, which I don't want to confuse you right now. 320 samples, we are going to 12 values. From 320 values to 12 values. These 12 values are our features. Okay. So once you extracted the features, we will go for modeling. So before that, I want to explain even other famous, popular features are bottleneck features. This is also very easy. The bottleneck features are based on neural networks. Okay. So how we train our neural network, we give an input, we have hidden layers in the network, and then output is generally classes. Means for speaker recognition, we give the speech as input, then each output is each class, means speaker 1, speaker 2, speaker 3. But there is a class of DNNs are there where your input and output are same. That means whatever input you are giving, you expect the same output. But what is happening inside? What happens is the input is modified into different values, right? So that means you are compressing here, since you have less number of them. Here, if your input is 320 samples, definitely the first hidden layer having less number of nodes, so they will come down. The input size will come down. So what we are doing is we are compressing the signal, and again we are decompressing. So what we call this is an autoencoder. So we expect the input and output is same, and if you train a neural network, artificial neural network with speech input and the same output, then we get this autoencoder. What we do is for feature extraction, we'll cut our autoencoder from the middle layer, and the output what we get here has been taken as the features. Those features are called bottleneck features. There's nothing more than that. I think you know how to train the neural networks. So just train the neural network by giving input and output same, train for huge speech, then cut your network by half and take the output of that hidden layer where you're cutting as your features. So these also you can directly use as a features. Okay. So these are the two features which you can use for your projects based on speech. Okay. Now, once we have finished our feature extraction, the next thing what we have to do is some modeling techniques. Okay. In modeling techniques, we have different modeling techniques in the literature. So I think you have gone through these things. Yesterday, Dr. Dilip has given, I think a few days back, he has given overview on Gaussian mixture models and hidden Markov models. I will only give an overview because I want to concentrate on the features side, which you people will scare. You think that the features is different, we won't do the projects, but I want to encourage you to do projects on speech. That's why I concentrated that on that side much. So we have different modeling techniques for speech-based systems. Okay, we have vector quantization, Gaussian mixture model, support vector machines, artificial neural networks. Recently, iVector framework has come for speaker recognition and language recognition. And speech recognition, we have hidden Markov models and artificial neural networks. I will give you a brief overview what these modeling techniques are doing. Okay. See, we have a data. So in vector quantization, what is the modeling technique? I said these are all statistical modeling techniques, right? Statistical modeling techniques means we extract some statistics from the given data. We have a data. Data means features what we have extracted right now. Take MSCC features. So these are the features. Now we want in vector quantization, what we do is we try to identify or try to compute we want to group this data into some groups, and for each group we will compute one representative vector. So these red color dots are your representative vectors. Generally these representative vectors in VQ are the means. So first you divide the data into groups, and for each group you compute the mean. So those are your representational data vectors. So in vector quantization, what you are going to do is you group your input data, that means your features, and for each group you compute the mean, and these are your representational vectors. So those are the statistics we extract for vector quantization. Now for Gaussian mixture model, what we are doing, Gaussian mixture model is also based, I won't say it is similar, but it is evolved from VQ. What in VQ, we are only extracting the mean. See, we have data like this, we are taking only mean. But in Gaussian mixture model, what we are going to do is, we also take into the consideration of the variance, how that group. See, we are clubbing the data into groups. Each group is represented by mean, not only by mean, but there is also called another statistic, that is variance. So how much this group is varied. Okay, one is mean and how much this group is varied. And one more thing we need to take consider here is, all groups are not equally represented. That means this group will have less features, this group will have the high features, right? Means high number of features. Okay, so there is a weight associated with each group, right? So in Gaussian mixture model, the statistics that we extract is not only the mean. In VQ it is only mean, but in Gaussian mixture model we extract for each group what is the mean, how it is, how that group is varied, how much that group is getting varied, and what is the weight, what is the strength of that, how many points are representing this group. Okay, these three are our statistics for Gaussian mixture model. Okay, the next one is support vector measure. In support vector measure, see, last two techniques are what we call is generative models. What means we extract those features from the given data. So we won't see what is the other data, what is the other class data. See, you have one class like one speaker's data. From the data you extract the features. But in the support vector measure, what we are doing is we have to have other class data also. Means data of speaker 1 and speaker 2, class 1 and class 2. Okay, and what we do is, here we want the extract features from the data, but what we do is we try to draw a boundary between the data. So these comes under discriminative modeling techniques. Okay, so we try to draw a discriminative boundary between the different classes, two classes with here. So, and the beauty of support vector measures is it gives the optimum boundary. Okay, optimum boundary means, see, we can have a line here. This line also will classify if you have a line in here, then this is also the data points on this side of the line is class 1, the data points on this side of the class is also class 2, but we'll get the middle line. That is what SVM gives. So how we are going to get this data? See, we have a data. Mostly this data is overlap data, what we are having. So if you have overlap data, your boundaries are non-linear. So it will be like this. If we have data, we will have non-linear boundaries. But if we project the data into higher dimension, where in the dimension, if the data is linearly separable, that is the theory behind support vector measures. We have a data which is not linearly separable in the given dimension. So what we do is we project this data into higher dimension where the data is linearly separable. So that projection will happen using kernel functions. Okay, kernel function. So you apply a function on this data, then what will happen? The data is projected into high dimensional data. In that higher dimension, the data is linearly separable. So the statistics here, what we extract using this support vector measure modeling technique is the kernel functions and its parameters. Okay, these are the parameters we extract if we use support vector measure. Now we go for hidden Markov modeling. So in hidden, I think you have your session on hidden Markov modeling. So what basically we do is, hidden Markov models are used for sequential modeling technique. Sequential modeling technique means, what happens is we need not see, we not only had to, we have different sounds like attending, we have different sounds like a, ten, ting, ing, right? So different sounds are there. We have to identify a, ta, and ding, not only identify, but that sequence is also important. First, keyword spotting or speech recognitions, what we not only identifying that variables, but we have to cater for the sequence in which we are identifying, right? So that's why these are a sequential modeling techniques. So for speech recognition, what I said, each one is a basic sound, and the order in which the basic sounds are appearing is also important for your speech recognition systems. Okay. So if your observation is Y1, Y2, YN, then there is an order. This is the order what we observe. So this order has to be considered. Okay. So this hidden Markov model does this. How it will do is, if you are in this state, if you are going from one state to other state, then there is a probability, transition probability exists. So with this transition probabilities will capture the sequential data. Okay. I think you have gone much into this thing in your previous session, so I'm not going deep in this. But what are the statistics? My thing is, from the data we are extracting the statistics. So what statistics we are extracting? So here, number of states, what all symbols means here, what are symbols with respect to speech? These are the basic sounds. What are the symbols in each state we can see, and what is the transition matrix? What is the emission probability? What is the probability of those symbols in each state? And what is the probability that you are at this state at that time? So these are all your statistical properties what we extract during hidden Markov model techniques. Okay. And the most popular thing as of today is the artificial neural techniques, neural networks. You know that a neural network is a simple neural network looks like this. It has one input layer, then a hidden layer, and then output layer, right? In hidden input layer, we give our input like our features. Hidden layer will, what it will do? It will transform the input into some other domain like our SVMs. It will transform our input into some other space where that space your features are linearly separable. Means we can, in that space we can say that this feature is we can say that this is this class and that class. So we can view like that also. So this is a simple neural network, but with respect to deep neural network, what is the difference? The number of hidden layers will get increased, but we have to see that as we are increasing, then network layers are the interconnections between the networks are also increasing, and the statistics what we are extracting here is the weights of the layers. Okay, the weights of the layers are what we are estimating while we are doing our training process, modeling process. Okay, so once we are doing this training, we extract this weights. So as we go deep in the network, the number of weights that you need to extract from the given data will always increase. So you have to see how much deep you are going. It depends on how much data you are having to train your system. Okay, that is one of the aspects you need to see. So I will explain you two neural networks, deep neural networks, which are used in speech recognition. So you know this convolution neural network. The beauty of this neural networks, artificial neural networks, is it not only do the classification task, but they also do extract the features also. So using, we need not have two steps like feature extraction and then modeling. Only one step you can do everything. That is the beauty of artificial neural networks, especially with deep neural networks. Okay, so with artificial convolutional neural network, which is quite popular, what we do is we have an input. So we apply a filter. Filter is nothing. We have a set of values. So what we do is we multiply these inputs, this filter values with respect to the input, and we will get a value. Just multiply these values with the input and sum them, and you will get one value. So this is what we filter. So how many filters we can apply? That is a variable. K is the number of filters. We have total 6 filters here in this figure. And then what is the stride? Stride means this filter is moving, right? Whether it is moving in an overlap fashion or non-overlap fashion. What is the step size of this movement of this filter? Like this movement, this filter will keep on moving across this input, right? So that will give you a stride value. And what is this F? F gives the size of the filter. What is the dimension? See, your input dimension is here 32 by 32, but the filter size is only 5 by 5. That is your filter size. And padding. Padding means your filter can start like this. Then what is your what that filter is representing this center point, right? So if you want your center point to be your corners, then here there are no values. At that time, generally the techniques what we do is zero padding. So we put some zeros here and we take a filter like this. Okay. So whether we are doing padding or not, here we are not doing the padding. So these are all the statistical parameters what we need to fix while designing your convolutional network, neural network. Okay. So this convolutional neural network will have this convolution. What we do is filtering. This process is the convolution. So once you do the convolution, you will get, for each type of filter, you will get one set of values. Then we do the pooling. Pooling means, again, a filter is there. In this filter, you will take one value or you will take average value. So one value is the max pooling, min pooling, different poolings are there. Generally, max pooling is popular. Average pooling. Average means you average this whole values in this filter. So like that. So one layer consists of one convolution and pooling layer in convolution neural network. So like that, you may have different set of layers. Here we have two feature extraction layers. Each feature extraction layer is a two layer again. That is, one is convolution layer, one is a pooling layer. After you extract the features, then what we do is a classification task, your modeling task. So this is a fully connected neural network. Like here, this is a fully connected neural network. So this will have fully connected. This is not fully connected here. This will have fully connected layer, and output is your classes. Like our, for speech recognition, different sound units. Okay. So the statistics, what we are extracting from the input data while training this convolutional neural network is this filter parameters and weights of the fully connected neural network. These are all the things what we extract. So as we go deep into this thing, lot of weights has to be estimated. So we need a lot of data while estimating this new convolutional neural network. But for speech recognition, we need not only identify what is our basic units, but we also need to identify the sequence in which they are appearing, right? It is not only identifying each unit, each basic sound unit, we have to identify the sequence. So that sequence will happen. How we capture that sequence with deep neural network. So this popular technique, popular neural network which are currently used is recurrent neural network. Okay, in recurrent neural network, what is happening is this one neural network is a CNN, convolutional neural network, and what we do is with some weight we again connect back to that same neural network. Means if we unwrap this recurrent neural network, recursive, right? You know the recursive technique, right? So same thing, with some weight again we will connect back to that same network. So there is a time sample with t-1, t and t+1. So same network we are using, means this network will identify what is the sound at t-1, what is the sound at t, what is the sound at t+1. That's how we estimate our sequence. Okay, again, so we will get not only the symbols, but we also get the sequence information using recurrent neural networks. This is how the artificial neural networks, deep neural networks, use it for speech recognition. That is recurrent neural networks. Okay, so the parameters that we estimate is again the filter parameters, weights, and weights for the recurrent network also. All these things are to be estimated using in your training process. Okay, now come to end of my presentation. So now I have given what all features are there in the literature, what all modeling techniques are there in the literature. So how you will design your intelligence system. That is the aim. Means if you are doing your project, what all aspects you have to consider. So first you have to identify what is your task. For that task, what is your features, ideal features. Okay, from the set of features I have given, you may take BNFs, you may take MFCCs, which is a 5-step process. So once you identify this thing, you have to identify the modeling techniques. See, modeling techniques we can identify. You can say that always the deep neural networks, now they are prevailing, I will use deep neural. But what is hampering you? The hampering is the amount of data available for training. So do we have enough data? Because the deep neural networks has some thousands of weights to be estimated. So do we have enough data to estimate those statistics from the given features? So if you have enough data, then you can go for more that thing. As if you have very, very less data, I will suggest you go for VQ also. Vector quantization also, you can go for simple things. You can do small, some 10-word recognition can do a good project for your this thing. You identify some 10 keywords, ask your friends to record those keywords, extract the features, and build simple VQ for the 10 words, and you can identify that thing. Okay. And again, you need to consider while doing operating environment, because as you are new, you may not understand that thing, but you can also, once you develop your system, you can see that where your system is performing badly, the kind of test sample, whether it is noisy or not. Okay, so you consider while extracting the features during training, you see your operating environment where you are collecting your data. So your data quantity and quality are important while designing and developing your system. Apart from identifying the feature techniques and modeling techniques you are using for developing your system. Okay. Now with this, I would like to end my talk, and I want to take questions if you have anything.
Okay, I request participants. Okay. Okay, if you have any queries, please ask Anil sir.
Sir, I have one question, sir.
Yes, sir. Please go ahead.
Actually, the frequency point of view,
Yeah.
when you hear some sound from outside,
Yeah.
it has some frequency rate.
Yeah.
That is what is the actually rate by which we hearing or listening some sound from outside? What is
Yeah.
the some frequency rate or range of frequency?
Yeah. We are human auditory frequency range is 20 to 20 kilohertz. Humans can only hear that frequencies. Apart from that, your eardrum will go soft.
Okay.
Okay.
For similarly, suppose CD quality or CD point of view, any range having there?
Sir, that's what. Sir, CD quality and all sample when you digitalize the signal. Okay.
Okay.
I said while explaining, when we are digitizing the signal, we are seeing the sample at some duration of time, equal interval of time. So every second we are taking 16,000 samples, right? I said one 16,000 samples. So now if you sample that rate with little bit higher, 22 kilohertz and 44,000 kilohertz, means if you sample per second, if you are taking 44,000 samples, that is your CD quality. Okay. 44.1K or something, means that means you are taking 44,000 values in 1 second. 1 second signal you are cutting 44,000 times, and each time you are taking a sample. If you are cutting more and more, means if you are taking more and more samples, the quality is always good. And what is the frequency depending on this thing? You know Nyquist bandwidth theorem. So
Yes,
what the Nyquist bandwidth theorem says is the rate at which you are sampling, right? So it is double the highest frequency, right? Suppose if I am sampling at 16,000 sample, the highest frequency that is present is only 8K, 8,000 Hz. Now, if you are sampling at 44,000 kilohertz, the highest frequency what we are having is 22,000 Hz, right? Now, 22,000 Hz is what our auditory system, human capacity is only up to 20K. That's why the CD quality is the very good quality. Why? Because it is covering whole entire human perceptual range.
Yes, sir. Yes, sir.
That's
so
why
that is a measured through sampling rate.
It is measured to sampling rate only. How many samples you are doing per 1 second of sample, 1 second of signal. CD quality is having 44 kilohertz.
That is standard sampling rate for CD quality.
That is standard, sir. That is standard.
Thank you, sir.
Welcome.
Sir, is this instrumental recognition is going to be different than the speech, sir?
No, sir. See, that is also, you can always see, I said, right, handset identification is there in our metadata. Like that, even, see, each instrument is having different keys, like piano and all, each key will have only one frequency.
Yes, sir. Definite frequency is there.
Right?
Yeah.
Mixing those frequencies will give the music to you.
Music, that's it, sir.
Right? Now, if you want to identify, there's a music identification we have, right? Previously in Airtel, I think they are giving one ad. If you hum your song, they will play back that song, right? Have you seen that Airtel used to give this ad that you hum your song, I will play back that song. So what they are doing, they are identifying music, what all tones are present. Based on that, they will identify your song.
So when compared to the speech one, this is going to be something easy thing, na, sir, comparatively, because no much dialects are okay, so no much frequency
Sir,
differences.
that is true, sir. But see, easy always I tell what are our challenges here is challenges with respect to the quality here always. The
Yeah.
data where you are humming in your room or you are humming on the road.
No,
If
if
you are
we
humming,
take directly from the instrument, okay, so then most
the
of the
instrument
cases, okay.
identification is very direct, sir. If you are directly doing from the instrument, there is no noise at all. And what is your class? How many classes are there? If you want to see in the instrument only, see, there are two things. In the instrument, how many keys you are having? Suppose take 50 keys. So you
Yes.
can identify the keys identification, you can do that. Else
Okay.
you want different instrument. One you take tabla, one you take piano, one you take this thing. Okay. Now each one will give different sounds. You can do that instrument identification. You can give these projects to your students if you have data. So that's why I want to encourage the students to take up this kind of projects. They should not have fear that this is all speech means some electrical work or electronics work, not computer science work. Okay, I request you to encourage them to do this thing because all the speech processing and the higher universities, they are in computer science department, not in other departments.
If I go with, okay, so the identification of the ragas kind of thing in a single instrument
Yeah,
also, it
definitely,
is
sir.
fine.
The identification of ragas is there. Professor Hamamuth is also doing from computer science department in IIT Madras. She is doing this identification of ragas.
Okay, sir. Thank you, sir.
Thank you. Thank you. Any more questions?
Babu sir,
Sir,
ask, yes sir, you want to ask something?
yeah, sir. First of all, greetings, sir.
Thank you.
Sir, congratulating for VFTSR Deemed University and IT department for conducting this, and I'm and Professor Viranja sir for coordinating this. Sir, I have one doubt that all these modeling techniques we will implement in MATLAB. Can we implement this in Python, sir?
Yeah, definitely, sir. Python, we have so many libraries, right now.
Okay. Okay, sir.
So
And sir,
not only
yeah.
MATLAB, okay, Python also. Sorry, I only mentioned MATLAB because I thought students are very
Yeah.
used to that MATLAB. Even Python also, all the libraries are there. You can easily use them directly.
Okay, sir. Sir, I was very much impressed on your explanation regarding human speech production diagram, sir. This is really very good,
Thank
sir.
you. Thank you.
Yeah. So, thank you, sir.
Sir, any more questions from the participants? Yes.
Parents sir, as no more questions from anybody, they will take forward and definitely some of them are take up some of the small activities in this area and they will publish papers what we expect.
Yeah.
Radhika madam. Hello, Radhika madam.
Here, thank you, Anil Garu. You have really given very good insight and also the research scope for developing the applications in speech intelligence systems. And I hope all the participants must have noted down the observations. And hopefully, by taking the suggestions, I think you can move forward and work on broad area in artificial intelligence. Thank you, sir. Thank you.
Thank you, ma'am.
Thank you very much for this session, sir. Okay, you have enlightened us about this machine recognition of printed text versus speech, machine versus speech recognition, and designing steps for speech intelligence systems. Okay, thanks for your talk, sir. I request Prema Moidu, sir, to give closing remarks.
This
Yes,
is
sir.
Prema Maidu, Professor, Department of IT.
One, sir, Krishna Kishore, sir, is it okay?
Okay.
Okay, okay, sir.
A very good evening to all. On behalf of Department of IT and VFTSR deemed to be university, I take this opportunity to propose a vote of thanks to those who have directly and indirectly contributed to this webinar on speech intelligence systems. At the outset, I thank our resource person, Mr. C.H. Anil Kumar, Scientist E, Center for Artificial Intelligence and Robotics, DRDO, Bangalore. We are enlightened with your knowledge and presence, sir. We are thankful to our Honorable Chairman, Dr. Lau Rataya Vignan Group, for his motivation to conduct webinars on various emerging technologies. I would like to thank our head of the department, Dr. K.V. Krishna Kishore, sir, for his enthusiastic support. A special thanks to the webinar coordinator, organizing committee, teaching and non-teaching staff for their unflinching support and coordination. Our heartfelt thanks to our participants for active participation. With these warm words and a kind message, we move to the end of today's seminar. Thank you.
Thank you.
Yes, sir. I am closing the session, sir.
Okay.
Thank you, all participants. Thank you.
Thank you.